I want to cover today, beginning statistics. So this book, as I said, it is on Leia. I posted that on Leia. It's a very good book, very easy book, very clear explanations, and also it will give you a reference for the things that you want to cover in this class. So let's just, today I would try to go past the introduction and descriptive statistics. I will try to cover as much as possible. It will be a review for you, so I may go through that very quickly. And hopefully I will reach the empirical rule and the Chebyshev's theorem. Let's do it. So whenever you're dealing with a statistical problem, you have a population. And this population could be, for example, a population of people. So that, let's say, population. It could be a population of cars. It could be a population of houses. It could be a population of, I don't know, some sort of animal. So, and you want to gather some information about this population. So what you do is, of course, you can go ahead and study the whole population if it's a small population and all the data within the population is available. You can do that, and if you do that, this kind of a study is called a census. However, in most cases, the population is very big. It would not be cost effective to try to measure every individual in the population. So what you do is you take out a sample from the population. So you take out a sample from the population. And the way you pick the sample is that you use a random method to pick the people from the population. So you can, for example, use a draw or a random draw, or you can use a random number generator and pick numbers. You can just label the individual in the population from 1 to whatever the size of the population is, assign each person a number, and then use a random number generator to take out a sample. So you randomly pick people and you move that to your sample. So this is the definition for a population. A population is any specific collection of objects of interest. A sample is any subset or sub-collection of that population, including the case that the sample consists of the whole population. So if every individual in the population is in your sample, then this kind of a study is called a census. Now, any questions so far? What is a measurement? A measurement is a number or attribute computed for each member of the population of a sample. The measurement of sample elements are collectively called the sample data. Each individual that is inside your population, you may be interested in some specific feature. For example, you may be interested in the height of students. You may be interested in the average of the students, in the grade point average, GPA of the students. You may be interested, imagine if it's an animal, you may be interested in the weight of an adult animal of this sort. If it's a car, if it's a population of cars, you may be interested in the price of the cars in your population. So these are called measurement. It's a certain feature that you want to study about your population. Another definition, very important one, you need to be able to distinguish between parameter and a statistic. What is a parameter? What is a statistics? A parameter is a feature of the population. So for example, these are the population parameters. So population parameters. One of them is the population size. Yes, we use uppercase N for that. Another parameter of the population is the mean of the population, or the average for all the individuals inside the population. So the mean, and the symbol for that is mu. Another parameter of the population is a standard deviation. So I'm going to call that STD, standard deviation. So we use sigma for that. So this is the symbol used for the standard deviation of the population, which is a measure of dispersion or variety in your population. I don't know, range. Let's use uppercase R for that. I don't know, median. Usually the Greek letter eta is used to describe that. So whenever you talk about the size of the population, the mean of the population, the standard deviation of the population, the range of the population, or the median of the population, these are population parameters, yes, which are usually unknown to us. We don't know that. So we are trying to study the population by a sample, using a sample, to find an estimate for these population parameters. It is possible to calculate the population parameters exactly if you do a census. That is, if you put everybody in your population, if you bring everybody in your population into your sample, then you can figure out what exactly mu is. However, in most cases, it's not practical or sometimes totally impossible to do that. Yes. So what do? We take a sample and we calculate some sample statistics. So what is a sample statistic? A sample statistic is a number that you compute from the sample data. So a population parameter is a number that summarizes some aspect of the population. What is a statistic? A statistic is a number that is computed from the sample data. Like, for example, your sample size, which usually is denoted by lowercase n. Your sample mean, that is, if you add up all the numbers in your sample and you divide by n, that would be X bar is usually used for that. Your sample standard deviation, usually lowercase s is used for that. Your sample range, we can use R for that. And your sample median, and for that usually X tilde is used. So this here is called hat, and this here is called tilde. So again, a population parameter is a feature of the population, which is usually unknown. A sample statistic is a number that you compute from the sample, but that sample statistic is usually an approximation for the population parameter. Yeah, like for example, X bar is an approximation for mu. S, the sample standard deviation, is an approximation for sigma. R, the range in your sample, is an approximation for the range in the population. And the sample median is an approximation, it's an estimate for the population median. These would be good approximations if they are close to the actual ones. And there are ways of measuring that we're going to learn later on. Any questions so far? What is a statistics? Statistics is the collection of methods for collecting, for displaying, for analyzing, and for drawing conclusions about data. Statistics is largely divided into two, the science of statistics is largely divided into two categories. We have descriptive statistics and we have inferential statistics. In this course, we mostly focus on descriptive statistics, which is the branch of statistics that involves with organizing, displaying, and describing data. We're going to learn how to interpret some charts like bar chart, pie charts, histograms, dot plots, box plots, and we're going to measure some sample statistics like measures of central tendency like X bar and mu, or mode. These are measures of central tendency. There are some measures of dispersion, which tells you about how much variety is there in your population, like standard deviation or the range or the interquartile range that you already know about. So this course, we mostly focus on this type of stuff, but there is a much bigger and much more important branch of statistics called inferential statistics. Is the branch of statistics that involves drawing conclusions about a population based on information contained in a sample taken from the population. So a big part of inferential statistics is modeling. So you can use data to create a model. So you can use something called linear regression or generally regression for that. You can create confidence intervals for your population parameters. You can do tests of hypotheses for the population parameters. You can study time series of different phenomena. So this is a very interesting branch called inferential statistics. This is a distinction between two types of data that you deal with statistics. When you're dealing with data could be qualitative, and it could be quantitative. Qualitative basically means not or non-numerical. And quantitative basically means numerical. So in the first section in Khan Academy, you did some exercises that in order to figure out which type of data is quantitative and which one is qualitative. Qualitative data is like categories. For example, blood type. Blood type is a qualitative data. Another example of a qualitative data could be, for example, level of education. If you have names for that, you say, for example, primary school, secondary school, college, undergraduate, graduate. So if you have this type of categories, and when you're collecting data about an individual, you just ask them, where is your level of education? And they just check. That would be a qualitative piece of data. Quantitative data are basically numeric data, like, for example, height, weight, blood pressure. This type of data, it's collected using numbers. So these are quantitative data. Is it clear the distinction between the type of data? These are basically categories, and these are numbers. But what is really important is that these are numbers for which you can do arithmetic. You can have some data that looks like numbers, but in reality it's qualitative. For example, you say, I don't know, type of membership. Yes, type of membership. You can say we have 3 memberships, type 1, type 2, type 3. Even though you're using numbers, 1, 2, 3 are numbers, this doesn't make this a quantitative data, because these are basically some type of membership, and these numbers, they don't make any sense. They don't make any numerical sense. So for example, you cannot, it doesn't make any sense to do, I don't know, type 1 plus type 2 is type 3. It doesn't make sense to do 1 plus 2. So these are apparently they're numerical, but in nature, this is not a numerical data. You might as well just, instead of type 1, 2, 3, you can say type A, B, and C, and there you can see that these are not quantitative data. So quantitative data are numerical data such that doing arithmetic for that data makes sense. For example, you can just add them up or subtract them, take average of them. That would make sense. But if you have some categories and you just call them 1, 2, and 3, it would be still qualitative data. Make sense? Any questions?
No, sir.
So qualitative data are measurements for which there is no natural numerical scale, but which consist of attributes, labels, categories. And quantitative data are numerical measurements that arise from a natural numerical scale. Like, for example, temperature is quantitative. Weight, height, blood pressure, these are all quantitative data. Also, I want to mention that qualitative and quantitative data can also be subcategorized. Your qualitative data could be nominal or ordinal, and your quantitative data could be for the qualitative data. Did you study about nominal and ordinal in Khan Academy?
No, sir.
Okay, so let's just not talk about them. I don't want to confuse you. Let's forget about it for now. So far, we just know about qualitative and quantitative. And so if I come across that in this book, I will explain to you what nominal ordinal is. Okay. So here we have something called the grand picture of statistics, which I almost talked about. We have a population. From the population, you use a random method to pick some people, bring them to your statistic, bring them into your sample. So you pick individuals randomly using a random manner, and you create your sample, and that would be your data, which could be qualitative or which could be quantitative. And based on this data, you calculate some statistics like the sample mean, like the sample variance, like the sample standard deviation, like a sample proportion, like, for example, the proportion of the students who have cars, the proportion of the students who are married. And then you use that sample statistic as an estimate for the population parameter. So you draw conclusions about the population using these sample statistics. So for example, your sample mean is an approximation or an estimate for the population mean. Okay, so that was chapter 1 of the book. Here you have some exercises. And you know, these exercises, I'm not gonna check whether you do them or not, but you'd better do them because for your exam, I'm going to use these exercises along with the exercises from Khan Academy for your final exam. Okay. So that is 1.2 overview of the book. So here we're going to learn about how data is organized in this book. Sometimes samples are given in this form, just as a list of numbers. Like, for example, this is the data obtained by measuring the age of 21 randomly selected students. So the ages have been listed, and they're not in the increasing order. So the first student was 18 years old. The second student was also 18 years old. Then we had 19, 19, 19, another 18. One of the students is the sample is 22. So you just list the sample data. Another way of representing the same sample data would be something called the frequency table, where you put your xi here and the frequency here. Like, for example, here we have a couple of students who are 17, we have 18, 19, 20, 21, and the oldest student seems to be 24. So we have 22 and also we have 24. There is no 23. Am I right? There is no 23. Then you can just count how many 17s you have. There is only two people who are 17 years old. That's called the frequency of this piece of data. So there are 2 students who are 17. That's the frequency of 17. That's how frequent 17 is, how many times it has been repeated. 18, 1, 2, 3, 4, 5, 6, 7, 8, 18s, and then you count the number of 19s, 1, 2, 3, 4, 5, 19s. And if you do that, you create something called the frequency table. So 2, 8, 5, 3, 1, 1, 1. So what you see here is a frequency table. Basically, from a frequency table like this, you can just list the numbers in increasing order, or from the list of the numbers in increasing order, you can easily create a frequency table. So these are equivalent methods of presenting the data. So for example, from this frequency table, it's very easy to see that 18 is your mode. Yes, it's called the mode because mode is the most frequent piece of data. There are 8 students in this set of 21 students who are 18 years old. So that makes 18 the mode of this sample. Basically, mode is the data with the highest frequency. So these are called frequencies. Yes, and the whole thing here is called the frequency table. And if your data are expressed in this form as a list, from that you can create a frequency table and vice versa. Is everything clear? Okay, so that was chapter 1 introduction. Let's move on to chapter 2. You have learned about dot plots, histograms. What other types of plots have you learned about so far in Khan Academy? Have you seen histograms?
Yes, sir.
Yes. Dot
Bar
plots?
graphs. Yes, sir.
dot plot,
Interquartile ranges.
yes, box plot.
Box. Yes,
Yeah, so these are some different types of visuals that we use in order to describe the data. Another very interesting one is something called the stem and leaf plot, which is basically very similar to the dot plot that you have in Khan Academy. Okay, I'm gonna talk about these three types of plots today: the stem and leaf, histogram, and histogram. We have two types of histograms. We have frequency histogram and we have a relative frequency histogram. So let's talk about these diagrams. What is a stem and leaf diagram? A stem and leaf diagram is a diagram that you create, as I'm going to show you, like this. So imagine you have this data, and the data is, suppose 30 students in a statistics class took a test and made the following scores. So they made this following scores. So there were one student who got 86, another student got 80, another student got 25, another one got 77, and generally there are 30 students and each one of them got a grade. And you want to understand, you know, you don't get a lot of information just by looking at a table of numbers, but you can easily rearrange this table of numbers and make it and create a simple plot from that, which gives you a lot more information. So let's find the smallest number here. What is this? There was one person who got 25. Yes, I think that's probably the lowest mark or the lowest grade, and the highest grade was 100. So I can use the tens as the stem. So I have all the 20s go in this row, 30s goes here, 40s, 50s, 60s, 70s, 80s, 90s, and the 100s, they go in this row. So for the 20, I have a 25. Yes, let's just take out these numbers one by one and write them down. 86, I have 86. And then 80, I'm going to put a 0 after that because it's 80. Then 25, I already put the 5 here. Then the next one is 77. So in the 70, I put a 7. 73. In the 73, I put a 3. 76, I put a 6. 100, I put a 0 in the hundreds. 90, I put a 0 in the 90s. 69, I put a 9 in the 60s. 93, I put a 3 in the 90. 90 here. 83, I put a 3. For 70, I put a 0 in the 7 row. 73, another 3 goes here. Another 3. 0 in the same row. 0 here. 83. A 3 goes here. 71. A 1 goes here. 95. 5. 40. A 0 in this row. 58. 8 in this row. 68. 8 in the 60s. 69. 9 in the 60s. 100. Another 0 here. 78. 8 goes here. 87. 97. 92. And 74. There you go. There is no room here, but there must be a 7 There must be a 4 also here. Okay, so this is called a stem and leaf plot. These are the stems. And the rest of the numbers, so these numbers here, the rest of them are called the leaves. And you can see that it's very similar to something like a dot plot. A dot plot would be like this. You have 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you just put a dot here. There is no dot for 3, 4, just 1 dot, 5, just 1 dot, 6, you have 3 dots, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 9, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And finally 10, you have 2 dots for that. Yes, it's very similar to a dot plot. The difference between a dot plot and a stem and leaf is that you can also see the leaves and you can read them. Like, for example, when you look at the dot plot, in the dot plot, you lose some information. Yes, when you have a dot plot like this, you lose some information. But when you look at the stem and leaf plot, you don't lose any information. You can just write down all the numbers by looking at the stem and leaf. You can just look at this, you say it's 25, then the next number is going to be 40, then the next number is going to be 58, the next number is going to be 69, then there are another 69, there's a 68. So you do not lose any information when you go from raw data into the stem and leaf. But when you're going from a stem and leaf into the dot plot, you lose some information. So when I look at the dot plot, I really don't know that these people who are in the 60s, what did they get? Did they get 60, 61, 62, 63? It's not exactly known to us. We only know that there are 3 people who are in this group. However, you can get a lot of information about how data is distributed just by looking at the dot plot. For example, it's evident that the people who got 70, between 70 and 79, they were, that would be the mode of this data set. Most of the people, exactly 10 of them, got a grade between 70 and 79. Another thing you can do is you can just put these numbers in order. So you can create another dot plot and you can put these numbers in order. For example, you put 8, 9, 9, or you put these numbers in order 0, 0, 1. You put them in order and then you get something called an ordered stem and leaf. So just I'm going to show you the stem and leaf. This is the stem and leaf that it's similar to the one that I created. And now if you order that, for example, here you can change the order into 8, 9, 9. Or here you can change the order into 0, 0, 0, then 2, then 3, then 5, then 7. If you do that, you have something called an ordered stem and leaf diagram. And if you replace every number with just a dot, you're going to have something called a dot plot. Are we good? So by looking at the dot plot or by looking at the stem and leaf plot, you learn about how data is distributed. You're good? No questions? Okay, now what is a frequency histogram? A histogram is when you have, so imagine for the same data, yes, imagine for the same data, I want to create a histogram. First, you need a frequency table. With a histogram, first you need a frequency table, and you need something called bins. And what are bins? Bins are intervals where your data, for example, you can say all the x's that are greater than or equal to 20 and less than 30, they go in the first bin. And all the data that are greater than or equal to 30 and less than 40, they go to the second bin. And then all the data that are between 40 and 50, they go to the third bin. Greater than or equal to 50, less than 60, the next bin. Greater than or equal to 60, less than 70, next bin. Greater than or equal to 70, less than 80, next bin. Or they're also called class. So these are called classes or bins. 80 less than 90, and let's say greater than or equal to 90 and less than 100 goes here, and anything that's greater than or equal to 100 goes to the last bin. Yes, so you can create bins like that, and then you count all the numbers that are within the first bin. So here you have something called frequency. It's simply the count within each bin. So between 20 and 30, when you look at this, you see there's just one person who got 25. So just one, the frequency is 1. Between 30 and 40, there was nobody, so 0. Between 40 and 50, there was just one person. 50 and 60, one person. Between 60 and 70, 3 people. Between 70 and 80, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. Then 1, 2, 3, 4, 5 in the next bin. 1, 2, 3, 4, 5, 6, 7 people in the next bin, and then 2 people in the last bin. So these are called frequencies, and from the frequencies you can create something called relative frequencies. Frequency. So what is a relative frequency? Is when you divide the frequency by the sample size. Sample size, and the sample size is the sum of all the frequencies, and it should be 30 because there are 30 students. Yes, if you just add them up, 1, 2, 3, 6, 16, 21, 28, 30. Yes, if you just add up your sample size, or n, lowercase n, is equal to 30. Now your relative frequency is going to be 1 over 30, 0, 1 over 30, 1 over 30, 3 over 30, 10 over 30, 5 over 30, 7 over 30, and 2 over 30. And if you add up all the relative frequencies, you're going to get 30 over 30, which is 1. And this is a check that you can easily do. You can just add them all up and make sure that the sum of the relative frequencies is 1. Is that clear? Frequency.
Yes, sir.
Frequency you get from the count of the numbers, and when you divide the frequency by the sample size, you get relative frequency. Now, from the frequency, you can create your histogram or the frequency histogram. From the relative frequency, you can create your a relative frequency histogram. So I'm going to show you how to create the frequency histogram and the relative frequency histogram. I'm going to keep these numbers. So a histogram is like a bar chart. Yes. So imagine here you have from 0 to 10, 10 to 20, 30, 40, 50, 60, 70, 80, 90, and 100. And here is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So the bar between 20 and 30, the bar is just 1 unit high. Between 30 and 40, there is nobody, so there is no bar. Between 40 and 50, again, there is just 1 unit high. Between 50 and 60, 1. 60 and 73, so I need to go up to here. 70 and 80, they're 10. So this is the longest or the tallest bar. Between 80 and 90, they're 5. So it's halfway. Between 90 and 100, there are 7. So it's up to almost here. And then there are 2 people who got 100. So it's going to be this high. This is a histogram. It's called a frequency histogram. Frequency histogram. Now, if rather than having a frequency histogram like this, if you're using the relative frequencies, you're going to have something very similar to this. It doesn't look different at all. It's going to be called a relative frequency histogram. So the relative frequency histogram is just like this. It's just like this for the x axis. 20, 30, 40, 50, 60, 70, 80, 90, 100. But the way you scale your y-axis, rather than having 1, you're going to have 1 over 30, 2 over 30, 3 over 30, 4 over 30, 5 over 30, 6 over 30, 7 over 30, 8 over 30, 9 over 30, and 30 over 30, which is 1. That's just going to continue up to here. And here is 30 over 30 or 1. Make sense? 1 over 30, 2 over 30, 3 over 30, 4 over 30, 5 over 30, 6 over 30. Sorry, it's 10 over 30. It's 10 over 30, not 30 over 30. It's 10 over 30, which is the same as 1 over 3. Yes, I don't need higher than 10 over 30 because my biggest relative frequency is here, which is 10 over 30. I don't need higher than that. So between 20 and 30, the relative frequency is 1 over 30. Between 30 and 40, nothing, then 1, then another 1. Then you have 3 over 30. Between 60 and 70, 3 over 30. Then you have 10 over 30, so it goes all the way up to 10 over 30. It's here. Then you have 5 over 30 for 80 to 90. Then you have 7 over 30 from 90 to 100. And finally, you have 2 over 30 for 100. So when you look at these two graphs, the frequency histogram and the relative frequency histogram, they just look the same. Yes, they don't look to be very different at all. But there is some interesting thing about the relative frequency table. Yes, imagine that from here to here is 1 unit. Yes, so each bean, or the width of each bean, let's say that is just 1 unit. Yes, then what happens when you multiply the base, which is 1 unit, and the height of each one of these bars? Yes, so each bar, the area of each bar, this area, is going to be 1 times the relative frequency. Yes, which is going to be exactly the relative frequency, because the base is 1 and you're doing 1 times the relative frequency. It's going to be the same as the relative frequency. So now there is a relationship between these relative frequencies that we have here and the area of the bar. So this becomes the area of it's very difficult to write with a mouse. It's going to be the same as the area of the first bar, or the area of this bar here is going to be exactly 3 over 30. So that's going to be the same as the relative frequency of the numbers between 60 and 70. Make sense? So I just wanted to mention this because I'm going to use it later, that there is this relationship between the area of the bars in a relative frequency table. That's not the case with the frequency table, but that is the case with the relative frequency table. There is a relationship between the relative frequency and the area of the bars. So how do we use that later on? This is the way you use it later on. So I'm gonna get rid of this and just keep the relative frequency. So imagine if I ask you, for example, if I randomly pick a student from this class. If I randomly pick a student from this class, what is the probability that his grade, his or her grade, is greater than or equal to, let's say, 90? Yes? The answer to this question is going to be whatever the area of, I'm going to use a red, it's going to be the area of these two bars, because these two bars represent the grades over 90 or more. If I calculate the area of these two bars, I get the answer. Yes, so the probability of x, let's say x is that random student. The X is the grade of that random student. Being greater than or equal to 90 is going to be the area of this bar, which is going to be 7 over 30, plus the area of this bar, which is going to be 2 over 30. 7 over 30, 2 over 30. It's going to be 9 over 30. So I just want you to remember this because this is going to be very useful later on. We're going to use that a lot. That when you have a relative frequency histogram, you can use the areas of the bars in order to calculate probabilities like this. I'm just going to give you another one and give you some time to calculate that. What is the probability that X is greater than or equal to 40 and less than 70? Calculate that. I'll just give you 1 minute.
So it is less than equal to 40 or greater than equal to 40?
It's greater than or equal to 40, but less than 70.
But you have put the sign of less than over 40.
Pardon me?
Sir, but the sign there is of less than equals to 40.
Yes. X is greater than or equal, not less than or equal to. X is greater than or equal to 40, less than 70, and you're calculating this probability. What is the confusion? You have to just calculate the area of this rectangle, the area of this rectangle, and the area of this rectangle. If you just add them up, you get the answer. It's going to be 1 over 30 plus another 1 over 30, and there are 3 over 30. That's the height of this rectangle, 3 over 30. So it's going to be 5 over 30, which is the same thing as 1 over 6. So that would be the probability. Is that clear? Any questions?
No, sir.
Okay. So so that was histogram. We talked about histogram, frequency, relative frequency histogram. It's going to be, I talked about that as well. Okay. And then if you have a large sample, your relative frequency histogram in many cases is going to be bell-shaped. And this turns out to be very, very important distribution in statistics. It's called the normal distribution or the Gaussian distribution, which describes usually things like weight, height of people, grades, IQ of people. If you look at the distribution of a large number of people, if you draw the histogram or the relative frequency histogram for that data, you will see that it's going to be bell-shaped like this. And as I just mentioned, when you have a relative frequency histogram, there's going to be some relationship between the area and the probability. So the proportion of the data that are between A and B is going to be the same as the shaded area for a relative frequency histogram. Not for a frequency histogram, but for a relative frequency histogram, there is this relationship. The proportion of the data that are between A and B is going to be the same as the area shaded here, just like the example we calculated here. Make sense? Any questions about this one?